Hello, welcome back. In the last session in number theory, we were discussing Diophantine equations. We saw a few equations that are falling in the category of Diophantine equations. Recall that a Diophantine equation is an integral equation involving some variables for which we require integer solutions. The main Diophantine equation that we discussed in the last session was linear Diophantine equation in two variables. We saw that a linear Diophantine equation in two variables is solvable if and only if the GCD of the coefficients divide the constant 10. Now we are going to see a few examples and we will be discussing that if at all there are solutions for a linear Diophantine equation, how many solutions do there exist and how to find all these solutions. Before discussing question about finding all solutions of linear Diophantine equations in two variables, we will see an example where the Diophantine equations are applied to a practical question. This question is attributed to Mahavira of ancient India. We will formulate Mahavira's puzzle. The question is known as Mahavira's puzzle. We will formulate Mahavira's puzzle into a linear Diophantine equation, try to find one solution for that and try to find all other solutions using the discussions that we are going to make today. Now we are going to see Mahavira's puzzle. So this is what is known as Mahavira's puzzle. The puzzle is the following. 23 weary travelers entered the outskirts of a lush and beautiful forest, and they found 63 equal heaps of plantains and 7 single fruits. They divided all of them equally. The question is to find the number of fruits in each heap. So in this question there are three numbers given to us. One is 23, next is 63 and other is 7. And using this we have to find how many fruits are there in each heap. So this is equivalent to assuming that there are 63 baskets in which equal number of fruits are kept and 23 people are there and 7 single fruits are kept outside the baskets. So altogether there are 63 into equal number of fruits in each basket and then plus 7, and that is going to be distributed to 23 people, 23 persons, and we have to know, we need to identify the number which we multiply to the 63. This is the question that we have. So if we start converting this question into algebraic terms, as usual, we use the variables x and y to denote the unknowns, and there are actually two unknowns. Even though we are supposed to find only one number, which is the number of fruits in each heap, there are actually two variables. We will see that how. So to start with, suppose x is the number of fruits in each heap, assuming that each heap contains equal number of fruits. So this we have to assume in each heap. So we are trying to translate this Mahavira's puzzle into algebraic notations, and for that we are using the symbol x to denote the number of fruits in each heap. Okay, therefore there are how many fruits are there in total? Therefore, if there are 63 equal heaps, each heap containing x fruits, so there are 63 x fruits in all the heaps together. But remember, there is an extra 7 fruits lying outside. So plus 7 fruits outside these heaps. So total number of fruits equal to 63x plus 7. We are supposed to find this x. But not that if we are just using the 63x plus 7, we may not be able to arrive at anything. We have to use something extra that is also given. It's given that 23 travelers are there. So we are going to make use of that 23. So we don't know how many foods are actually distributed to each and every person. Of course, we have to find the number of foods in each heap, but there is another thing that it's given that the foods are distributed equally to all the 23 travelers. Therefore, if we suppose that y is the number of fruits given to each and every traveler, then there are total 23 into y foods. If y, so we have the second variable here, y is the number of fruits each traveler gets. Then how many foods are there? Assuming that all the foods are distributed, then there are 23 into y foods. This 23 into y includes all the foods and heaps and the 7 single foods. But now, note that all the foods are distributed, therefore 23 y foods are all distributed. But we have seen that here we have total number of fruits is 63x plus 7. Therefore, the total number of fruits available is equal to the total number of fruits distributed. Therefore, 63x plus 7 equal to 23y. Now we have an equation, and if we take the variables to one side and the constant part to the other side, we get 63x minus 23y equal to minus 7. We know that this is a, and one more thing is that the y is the number of fruits distributed to each person. Therefore, y is a full number, assuming that we are not cutting any fruit. So y is a natural number. X is the number of fruits in each heap. Therefore, x is a natural number. So we want to know the number of fruits, that is x. But once x is found, y also will be found. Once x is found, y also will be found, or once y is found, x also will be found. Therefore, once we find one of the variables, the other variable value will be automatically obtained. So we need to actually solve it for just one variable, and the other value also will come. But okay, if you want to find just one value, one way is to probably separate the variables into two different sides and write an expression like this. So if we just take 63x plus 7 is equal to 23y, therefore y will be equal to 63x plus 7 by 23. Of course, we can give we can solve this by trial and error by giving x is equal to 1. If we give x equal to 1, then this is going to be if x is equal to 1, x equal to 1 implies y equal to what? Y is going to be equal to 63 plus 7 by 23, and this is equal to 70 by 23, but this is not a natural number. Therefore, we cannot accept this because we want the solution to be a natural number. Suppose that we continue this process. We just try with, we know that x is the number of fruits, and therefore x must be at least 1. So if we continue this process, we have, suppose we put x is equal to 2, then we get y equal to 63 into 2 plus 7 by, it's going to be 20, this is 23, this is equal to 126 plus 7, that is 133 by 23, and this is also not a multiple of 23 because 23 into 5 is going to be 115, and this is also not a natural number. If you try x equal to 3, I am just writing x equal to 3, then we get y equal to 63 into 3 plus 7 by 23. Now, instead of keeping on computing like this, probably I will ask the help of Sage Math to do these computations for me so that I can easily find out. Now I am going to use Sage Math. Stage math is here. I am going to just write the expression. My y is equal to, I'm defining, otherwise if I call y to be f of x, then my f of x is nothing but 63 into x plus what is the number, 7, and that is divided by 23. Now I am going to ask for 1, 2, 3, etc. for x in 1, 2, okay, I will try up to 10 and see if I am getting something. 10. I am going to ask Sage Math to print f of x, and of course x also. So x and f of x are going to be printed. Let me see what is the result. So I'm going to run Sage Math. Run. Okay, so I'm getting the numbers to be this 1 and 70 by 23. This is exactly the same thing that we got when we tried the computation manually, and after that 133 by 23, this is also a rational number. And next x is equal to 3, then I'm getting y to be equal to 196 by 23. X is equal to 4, I am getting 259 by 23, still a rational number only, not an integer. And now at 5 I am getting x is equal to 5 and y is equal to 14. So this is probably the solution that I am looking for. X is equal to 5 and then y is equal to 14. So this is the number that we want. You keep trying with x is equal to 4. I forgot what the value was. Just try to find it. Now for x is equal to 5, we are getting y to be equal to, this is a rational number. This is also not in the natural number set. This is also not in the natural number set. But this is equal to 14 and this is in the natural number set, and therefore the number of fruits in each heap is going to be equal to 5, and to each traveler we are distributing 14 fruits. Okay, let us see whether this tends to be correct or not, because we can just try 63x plus 23, 63x plus 7 equal to 23 by, let us see if it's satisfied or not. So 63 into 5 plus 7, that is going to be equal to 315 plus 7, that is 322, 315, 7. Okay, now what is the next number? 23 into 14. So 23 into 14 is going to be equal to, this is now 23 into 10, that is 230, 4 into 23, that is 92, 230 plus 92, that is 322. Therefore, these two are equal. So, Mahavira's puzzle, the solution is each heap contains 5 fruits, and of course, in addition, we found the number of fruits distributed to each traveler, which is equal to 14 fruits. So this is the number we have. This is the solution. We don't actually know that whether if this is the solution for Mahavira's puzzle. At most, what we can say is this is a solution for Mahavira's puzzle, and we got one solution to be 5 fruits and 5 fruits per heap and 14 fruits per traveler. That is the distribution that we have made. Okay, now if we translate this into, okay, of course we have already translated this into linear Diophantine equation of the form 63x minus 23y equal to minus 7. Now we have already seen one previous knowledge we already have. We know this. We remember that we solved Mahavira's puzzle by arbitrarily putting values for x by like 1, 2, 3, etc., and by then locating y equal to some integer. That is what we did. So that is not actually a clever way of doing things. By trial and error, if you are trying to achieve something, we may achieve something in certain problems, and we may not get anything in certain other problems. So we cannot use that technique every time. So we know this. A linear Diophantine equation ax plus by equal to c is solvable. Solvable means there exists integer x and y for xy in z if and only if d divides c, where d is the GCD of AB. So this fact is known to us. Okay, we will make this into we will give off some color for this result. This is the result that we discussed in the last class and we proved it. Okay, now what about Mahavira's puzzle? This condition this is an if and only if condition necessary and sufficient. Therefore, for the solution to exist, this condition must be satisfied. So, in the Mahavira's puzzle case, we have in the Mahavira's puzzle, we have 63x minus 23y equal to minus 7. And what is the GCD of 63 and 23? You will just see. The question is now find 63, 23. So what is GCD? We are going to use Euclidean algorithm. So 63 equal to 23 into 2 plus this is 46. Now remaining is 17. Now 23, we are following the steps in the Euclidean algorithm. 17 into 1 plus 17 into 1 plus 6. Now 17 equal to 6 into 2 plus 5, and now 6 is equal to 5 into 1 plus 1, and here we are getting the GCD, the remainder to be equal to 1, and this is the least possible positive remainder, not zero remainder, because after 1, of course we can go to the next step and we can see that. So 5 is equal to 1 into 5 plus 0. So we got 0 here, this is the 0 here, this is the GCD. Therefore GCD of 63 and 23 is nothing but it's equal to 1. So the GCD is 1. 63, 23 is 1, and of course 1 divides minus 7. Therefore solution xy belongs to z. X is for the Mahavira's puzzle. So our theory actually guarantees that solution exists, and of course we have observed that by trial and error we actually found a solution, and therefore a theory is not in contradiction with what we observed. So there is a solution, definitely. Now instead of trial and error, how can we find the solution? That's the question now. So instead of trial and error, how do we find the solution? How to find a solution for 63x minus 23y equal to minus 7 without using the dangerous technique of trial and error. So this is the question we have. How to find a solution for 63x minus 23y equal to minus 7. But we should not use the trial and error method, but we should devise some method based on our experience on concepts like GCD, LCM, etc. So trial and error method not permitted. So in that case, how do we find a solution? Okay, the technique is going to be something like this. So we have to solve 63x minus 23y equal to minus 7. But we know that 63, 23 is, its GCD is 1, since 63, 23, GCD is 1 by Bezos identity. There exists m, n in integers such that 63 m plus 23 n equal to 1. This is quite clear. Now, but we need 63x minus 23y equal to minus 7. So we are slightly modifying this. Therefore, we need minus 7 on right side. So to get minus 7, we need to probably multiply the left side also with minus 7, right side also will be minus 7. Therefore, 63 into minus 7m plus 23 into minus 7n equal to minus 7. But here we actually need minus 23. So just to get that, 63 into minus 7m minus 23 into 7n equal to 7. What is this m and n? M and n are the Bezos coefficients for 63 and 23. So we have to find m and n first, and once we find m and n using Bezos identity, m and n as guaranteed by the Bezos identity, we will be able to find this minus 7m and 7n as the solution for the Mahavira specific. So now our question is to find m and n such that 63m plus 23n equal to 1. So now the question is find mn integers such that 63m plus 23n equal to 1. So for finding such an m and n, we are going to use the extended Euclidean algorithm, which is a manipulation of row-like operations on the 63 and 23, which will be clear once we explain how we are actually proceeding. Okay, so we need to express 63, 23 linear combination equal to 1. So we know that 63 is equal to 23, the smallest number, 23 into 0 plus what is the next number? 63 into 1. So we need 63m plus 23n, therefore we call this as n. This is 0 is n, this is m. Now 23, if we write in the same way, this is 23 into 1 plus 63 into 0. Okay, now from 63 we are going to subtract the largest 23 multiple, that is 63 23 into 0 plus 63 into 1. Now 23 into 2 is the largest thing that we can multiply, that we can subtract. So this is 23 into 0 into this is not 0, this is 23 into 1 into 2. We are multiplying with 2 on this equation. So this is the first step. Second step, we are going to subtract 23 into 1 into 2 plus 63 into 0 into the same 2. So if we subtract, we get something like 63 minus 23 into 2, that is 17. This is equal to, this is 0, this is once again 23 into, what are the coefficients that we are subtracting? 0 minus 2, therefore it is minus 2 plus 63 is common. What about the coefficients? 1 minus 0, therefore this is 1. But now if you observe carefully, just see that only on the left side we are multiplying and subtracting. On the right side we have 23 into something, 23 into something. So 23 is common, and therefore we are manipulating only the multiplied factors. These are the only factors we are concentrating on here. So the 63 is 23, 23. We need not actually write each and every time. So we will just drop that and we will only manipulate the coefficients on the right side of the equality and the actual number on the left side. So now, therefore, we will write 17 minus 2, dropping that 23. Remember that there is a 23 multiplication here, and instead of writing plus, we will just leave it. So this is 1. 17 minus 2, 1. Now see that from 63 we subtracted multiples of 23. Now from 23 we are going to subtract multiples of 17. So 23, we are writing only the coefficients here. So 23, and after that this is 1, this is 0. Just writing 1 here, 0 here. How many 17s can be subtracted? 17 into just 1. So minus 2 into 1, 1 into 1. So if we subtract, so here there is a subtraction, here there is another subtraction. If we subtract, we get this to be equal to 6, 3 and minus 1. Now we need to subtract the largest possible multiple of 6 from 17, minus 2, 1. So we are just rewriting that 17 minus 2. So this row 17 minus 2, 1, and from that 6 into 2, 3 into 2, this row into 2, this into 2 I am subtracting, 3 into 2 minus 1 into 2. So on subtraction, this is subtraction, we get 5 minus 8, 3. Now from 6, 3 minus 1, we will subtract as many multiples of 5 minus 8, as many multiples of 5 that's possible. So 6, 3 minus 1 is the next one. 6, 3 minus 1. From that 5 can be subtracted only one multiple. So 5 into 1, minus 8 into 1, 3 into 1. Minus 8 into 1, 3 into 1. If we subtract, we get 1 equal to, this is 3 plus 8, that's 11. This is minus 1 into 3, minus 1 minus 3, that is minus 4. See, this is actually the GCD. And remember that here it is 23 into, this is into 23 is here, into 63 is here. Therefore what we got finally is that 1 equal to 23 into 11 plus minus 4 or 63 into minus 4. We may check by multiplying 63 into minus 4 and 23 into 11 and adding, we may check that this right side is actually equal to 1. So we have found a solution for the modified question. The modified question is that to find m and n such that 63m plus 23n equal to 1. So m is equal to minus 4. Therefore m equal to minus 4, n equal to 11. Now what is the solution? What is the solution for Mahavira's puzzle? We have already seen that. Solution for Mahavira's puzzle is going to be, it's equal to minus 7m. So from here, solution for Mahavira's puzzle will be minus 7m and 7n. Therefore, here we have Mahavira's puzzle solution is minus 7m, 7n, and that is nothing but equal to minus 7 into minus 4, that is 28. 7 to 11 is 77. So this is one. So what is meant by this? So number of excess number of rows each heap. equal to 28. Each traveler will get 77. But this is actually really surprising because previously we have seen that each traveler will get how many? So we have seen that each traveler will get each heap contains 5 fruits and each traveler will get 14 fruits. 5 and 14. These were the numbers. But now here we are getting the numbers to be equal to 28 and 77. So that means that the solution for a linear Diophantine equation, of course in the case of Mahavira's puzzle also, that is not going to be unique. Solution for, so the observation is the following. Solution for ax plus by equal to c need not be unique, because we cannot say that strictly that there exists one x and one y and only that x and y in such a way that x plus by is equal to c is satisfied. We have already seen that for the Mahavira's puzzle, which is a linear Diophantine equation, we have found two solutions for the linear Diophantine equation. Therefore, the question now is, when is this solution going to be unique? And if the solution is not unique, how many solutions do there exist? And how to find all the solutions? These are the questions we have. So the questions we are going to ask are the following. And a linear Diophantine equation by is equal to c has solution, this we know, if and only if d divides c, where d equal to GCD of AB. Now when is this going to be unique? That means solution is going to be unique. If not unique, how to find number of solutions and all the solutions. So these are the two questions we have. When is the solution? We know that there is sufficient necessary and sufficient condition for the solution to exist. That is, ax plus by is equal to c. The GCD of a and b must divide c for the solution to exist. And when the GCD of a and b divides c, definitely the solution exists. Next thing is, when is the solution going to be unique? And if the solution is not unique, how to find the number of solutions and all the solutions? These are the two questions we have, and we are going to discuss these questions, and we are going to completely settle down these questions now. We are writing down the main question once again. Find all solutions of ax plus by is equal to c or otherwise of the, since we need integer solutions, we should clearly mention that this is a linear Diophantine equation. By all solutions of the linear Diophantine equation ax plus by is equal to c, and for simplicity we are assuming that a, b are natural numbers. Okay, so to start with, we denote the GCD of a and b by d. So in the first case, we know that if d does not divide C, no solutions exist, because necessary and sufficient condition for the solution for ax plus by equal to c to exist, D must divide C. No solutions exist for, we will call this as equation 1. So in the next case, therefore, we have to assume that D divides C. D divides C. Then we know that by Besso's identity, there exist m, n integers such that am plus bn equal to D, not C. This is equal to D. But D divides C implies that there exists an integer k such that C is equal to k into D. So from this am plus bn equal to D, if you multiply k on both sides, we will get C on the right side. So k into am plus bn is equal to kd, or a into km plus b into km equal to c. Therefore, if m and n is mn is a solution for am plus bn is equal to d, then we can we have a solution for x plus by is equal to c to be equal to kn. Therefore, if mn is a solution for ax plus by is equal to d, then km kn, this is actually an ordered pair, is a solution for ax plus by is equal to c, where c is equal to kd. So it is enough to find solution for ax plus by is equal to d, and from that we can find solution for am plus bn, ax plus by is equal to c. Okay. So when d divides c, definitely there is a solution. That's guaranteed. Now we have to find if there is one solution. We know as in the case of Mahavira's puzzle, we know that there exists more than one solution. Suppose that x naught y naught is one solution, which is probably equal to km kn. Right? X naught equal to km, y naught equal to kn. Therefore, x naught y naught is a solution for equation 1. See that the equation 1 is nothing but that is equal to ax plus by is equal to c. Fine. So these are solutions. X naught y naught will satisfy the equation. Therefore, ax naught plus by naught equal to c. Now suppose that we want to modify this x naught to, suppose that another solution exists there. We don't know how many solutions are there. We want to see if at all solution exists, how do that look like, etc. So how will you get another solution? So for getting another solution, we may need to modify this x naught. Suppose we change x naught to another integer x1, then naturally we may have to change this y naught also, because for the equation to balance, probably we should change y naught to y1. So the new values that we are going to substitute on the left side is x1 and y1. Now see that x1 and x0 need not be the same, y1 and y0 need not be the same. So suppose that we relate them in the following way. Suppose x1 minus x0 is equal to some k1, and suppose y1 minus y0 is equal to k2. Remember that k1 and k2 can be even equal to 0, but in that case x1 is going to be equal to x0 and y1 is going to be equal to y0. Or this implies that x1 equal to x0 plus k1, y1 equal to y0 plus k2. If x1, y1 are solutions, if x1, y1 is a solution, then a x1 plus b y1 must be equal to c. But what is x1? x1 is nothing but, we have already seen, x0 plus k1. Therefore a into x0 plus k1 plus b into y0 plus k2 equal to c. Now we expand this, so ax0 plus, if we take this by0 also to this side, by0, now ak1 plus bk2 equal to c. Now this itself is c, so here already there is a c, therefore ak1 plus bk2 equal to 0, or ak1 equal to minus bk2. Now see that we will concentrate on the left side. ak1 is a multiple of a divides a k1. Now b divides minus bk2, b divides minus bk2, therefore b divides ak1 because they are the same, therefore a and b divides ak1. But we know that if a divides sum and b divides sum, then the LCM of a and b also divides sum. We have already observed. So this we have observed. If a divides sum and b divides sum, then LCM of AB divides sum. So using that, therefore, if L equal to LCM of AB, then L divides A K1, or A K1 is equal to Q into L for some Q integer. So we got A K1 is equal to this, or now we have to find K1 because A is known, B is known, therefore L is also known. Now we need to find K1. So K1 is equal to Q into L by A, but note that A and B are positive. Then LCM into GCD is equal to AB. Therefore, K1 equal to Q into L is nothing but AB by D. AB by D by A, that is equal to Q into B by D. Now what about K2? K2 can be actually found directly using the relation that A K1 is equal to minus B K2. A K1 equal to minus B K2 implies K2 equal to minus A K1 by B, but now minus A by B, what is K1? Q B by D, so this is equal to minus Q A by D. Therefore, if x1 y1 is another solution, then x1 is equal to x0 plus k1, that is equal to x0 plus q b by d. y1 is equal to y0 plus k2, that is equal to y0 minus q a by d. So if x1 y1 are two solutions, then x1 is going to be, x1 y1 is a solution other than, or maybe, see, if we put q equal to 0, we will get x0 y0 itself. Therefore, if we have x1 y1 a solution, then x1 y1 will be related to x0 and y0 in this way. So this is a very important result we have. If at all we have a solution, it looks like this. Let us color it. So we have another solution will definitely look like this. Now the question is, see, here we have found, we have assumed that x1 y1 is a solution, and then we try to find out one q and one q came, but we don't know for, see, here we have q, where did we start our q? For some q belongs to z is what we have taken. Therefore, it is not very clear that if we vary the values of q, if we keep on varying the values of q like 0 plus or minus 1 plus or minus 2, we will be getting solutions is not actually guaranteed. But of course, we know that if q is equal to 0, this is a solution. But q is equal to 1, q is equal to 2, we don't know if it's a solution or not. Therefore, what we have observed is every solution will look like, therefore, if x0 y0 is a solution for the LDE ax plus by is equal to c, assuming that a, b are natural numbers, then any other solution will look like x0 plus q a by d, y0 minus q, oh sorry, this is q b by d, what is written here, q b by d, and y0 minus q, here this b a by d. So if something is a solution, it will look like this. But we don't know whether every number looking like this will be a solution. We don't know. Next question. If R, S look like x0 plus q b by d, y0 minus q a by d, is RS a solution, or is x0 plus q b by d and y0 minus q a by d a solution for every q? So if this is a solution for every q, that means that there are infinitely many solutions. But what we have seen just now is that if there is a solution, it looks like this. We don't know if there is a solution or not, we don't know exactly. So we are going to see if numbers of this form is going to be a solution or not. So just remember these numbers, x0 plus b q b by d. Okay, we will just copy x0 plus, copy this. So we will just try to substitute these numbers into the equation. A into x0 plus qb by d, and we will probably move this also, plus b into, okay, what is the value of this? So if we expand, this is going to be ax0 plus a qb by d, a qb by d plus b y0 minus b q a by d, but these two numbers are the same, so we cancel. Therefore, this is equal to ax0 plus b y0. Therefore, this is equal to c. Therefore, for any q, this is going to be a solution. Therefore, if x0 y0 is a solution, then set of all solutions is x naught plus q b by d y naught minus q a by d, where q belongs to z. So how many solutions are there? Infinitely many solutions if one solution exists. So if there is one solution, it is guaranteed that there exists infinitely many solutions. This is what the conclusion of our discussion. Now going back to Mahavira's puzzle, we will try to find all solutions for Mahavira's puzzle now. Back to Mahavira's puzzle. So what was the conclusion there? There we got 63 into 28 minus 23 into 77 equal to minus 7. So to solve it, we need to get a and b to be positive. Therefore 63 into 28 plus 23 into minus 77 equal to minus 7. This is our x naught, this is our y naught. So the other solutions are, or all solutions are, this 28. So what is b in this case? B is the BCD of 63 and 23, that is equal to 1. And now a is equal to 63, b is equal to 23. So this is x naught plus q into b by d. B is nothing but 23 by d, that is 1, and y naught plus not y naught, not this is not plus, y naught minus q into a by d. A is nothing but 63 by 1. Therefore this is equal to 28 plus 23q and minus 77 minus 63q. So if you put q is equal to 0, we will get 28 and minus 77, which is the solution here. Q is equal to 0, we will get solution as 28 minus 77. But what about q is equal to 1? Q equal to 1, the solution is 28 and q equal to minus 1, because we want, remember that we have previously got one solution to be 514. So to get something less than 28, we need to subtract q. So q equal to minus 1, so this is going to be equal to 5. Q is equal to minus 1, therefore this is going to be equal to minus 1 to 63. Minus 1 to minus 63, that is plus 63 plus 70 minus 77, therefore this is going to be equal to minus 14. Remember that here we had minus 23, therefore we get exactly the same solution that we obtained in the trial and error case. So we got exactly the same solution here, and therefore we have completely settled Mahavira's puzzle. These are all the possibilities for the number of fruits and number of fruits in each heap and the number of fruits each traveler may get. There are infinitely many solutions for Mahavira's puzzle. And of course, the least possibility for x is going to be equal to 5, because if you keep on increasing q, you will be getting 28 plus 23 into 1, 28 plus 23 into 2, etc. Therefore, the larger numbers will be turning up, and the least number of fruits is going to be 5, and in that case 14 fruits will be given to each traveler. So we have completely explained all the solutions for the linear Diophantine equation in 2 variables. And with this, we are stopping this discussion. Thank you.